Last class before spring break. Woo! Okay, so now we're going to talk about stress due to shear force. You know, we have, so we're on stresses and beams. Whoops. Three, one, okay. And it works like this. The total stress is the stress due to internal tension, plus the stress due to internal bending moment, plus the stress due to shear force, plus the stress due to torque. And we've talked about this one and this one. Once we talk about shear force, so there aren't too many examples that you can do where the only internal loads are tension and bending moment, but there are a lot of examples where the only internal loads are tension, bending moment, and shear force. So once we do this one, we can do a lot of stress and beam calculations completely, okay? And so now we're talking about stress due to shear force. And if this is a blown up cross section of the beam, and say we want to calculate the stress at this plane, okay? Then think of a long, small, so the coordinate system that we're using is like this. This is going to be good today, Joy. Okay, so there's the coordinate system we're using. And for shear force, everything along the z-axis, so every line along the z-axis has the same stress due to shear force. So I'm going to think of stress elements. You know, we think of a stress element as a cube, but this is going to be like a long, skinny rectangle. You know, this is our stress element. Okay? Like, that's a whole row of stress elements. That's a good way to say it. Okay, and the shear force on that red plane is like this, right? That's the sign convention of okay. So what do the stresses look like that shear force creates? It looks like this. Okay, that makes sense, right? It's in the same direction as the shear force. And so if we look at this just totally from the side, look at this element this way in the XY plane. The stress due to the shear force is this way, this way, this way, and this way. Okay, so shear force V produces a shear stress in the XY, XY element of stress. Okay, but this picture, if you understand what I'm trying to draw on this picture, that explains why it's an XY shear stress. Okay, and also it explains why you're going to see with the formula, if you have a positive shear force, that leads to a negative XY shear stress. Okay, because this is a positive shear force going down. And this is, like if you look at the X face, this is in the negative Y direction. So that's a negative XY shear stress. Okay, are you with me on that? Okay. So before I get into the formula, I have to give you the requirements for the beams. Remember what the requirements were for, what were the requirements for the beam for stress due to tension and compression?
Prismatic and symmetric.
That was for the bending moment. So I'm getting to that next. But for internal tension and compression, there's no restrictions. It works perfectly well. It's a simple calculation. But okay, for the bending moment, then that's where we start having restrictions on things. It has to be straight. It has to be prismatic, so the cross-section doesn't change along the length. And it has to be symmetric about the y-axis. Okay, so now here's the beam requirements for stresses due to shear force. So first, so let me say it like this. There are only two beam cross sections we can work with. Two that we can do. The first one is a rectangular cross section. And our approximations, our calculations are going to be best as the height of the cross section gets bigger compared to the width, or the base, let's call it. Okay, so if it's short and fat, shorter and fatter than a square, you probably don't want to trust these results. Let's just call a square the kind of cutoff for whether we're going to trust these results or not. But the taller and skinnier it is, the better our results are. Or the only other option we can do is a circular cross section. And if we have a circular cross section, as if this wasn't bad enough, we can only do it at the neutral axis. Okay, so like whatever group was assigned to figuring out how to deal with internal shear force really let us down on this. There's not that much we can do, you know. WTF. But at least, like, why would we care about what's happening along the neutral axis? The stress is biggest along the neutral axis. So at least we can calculate the maximum shear stress due to the shear force. Okay. So at least the stress due to shear force is the biggest there. You know what I'm saying? So at least there's some reason why that would be more important than along some other line on the Okay, well, those are the restrictions. So the formula for the XY stress due to the shear force V says tau XY is equal to negative V times this new calculation, area related calculation. We have to talk about capital Q times the area divided by the area moment of inertia divided by the thickness of the thing at that point. So this is the width of the cross section. At the desired location. This is the area moment of inertia. And this we need to define. And I don't know any other name for it except Q, but I'm sure it has some name. And like all these other stresses, you can trust the sign that you get. So if you use the sign convention of the shear force, you'll get the correct sign for the shear stress. You can see this negative says that it has the opposite sign of the shear force, and that's what we saw in this picture, or this picture. Okay, so now to calculate this variable Q, I'm going to draw a cross section, and you can calculate this for any shaped cross section. If you calculate the centroid of your cross section, you can define the neutral axis. And let's say that you want to calculate the stress due to shear force along this line. Okay? Then calculate the area above that line. Find the centroid of the area above that line. And again, we're only worried about height, so we don't care about where it is horizontally. Calculate the distance d from the neutral axis to the height of this line, so I'll call this d. And then q is equal to that area times that distance. So I think that picture makes it clearer than words do, but so once you have the neutral axis, figure out where you want to take your stress. Find the vertical centroid of the area above that. Multiply the area above to the distance, and that's your Q. Okay? Like, what does that mean physically? It doesn't mean anything physically. It comes from a very long, complicated derivation of this thing, and it's just some mathematical terms that get grouped together. Okay? So there's not really any way to make physical sense out of it, as far as I can tell. Okay, here's an interesting factoid, cool factoid. If you calculate Q using the area above your desired line, you get the same thing as you would using the area below your desired line. So you can do it either one of those two ways. And I'll show you what I mean. Okay, so let's say your cross section is like this, and this is your neutral axis. Okay, and this is your line of interest. So this is where you're trying to calculate the stress. Then you could do this. And this is your D. And this is your A. Or There's your neutral axis. Here's your desired line. Make this your A. The centroid is going to be somewhere, maybe that was a little too low, but it's going to be somewhere below your neutral axis this time. And this is your D. And how could those two be the same? Well, you can see on the right, D is smaller, but area is bigger, you know? And those offset each other and you'll get the same answer. One thing I want to point out here, I mean, we're talking about an area and a distance, so this always has to be positive. Okay, so in calculating the stress, V can be positive or negative. That's the shear force. Everything else has to be positive. So you always have a stress that's opposite the sign of the shear force. Okay, let's see. So this is going to be the first example we do with a shear force in it. And this is the first time we've been able to do really, I mean, I had sort of like carefully cooked up examples, but this is the first example that looks like a normal internal loads problem where we can calculate the full stress tensor. Okay, we just can't do it for torque yet. And then that's the next thing we'll do. Okay, so let's do a beam that's cantilever at the right side so that we don't have to calculate the external loads. And let's say it's 2 meters long. And we're going to calculate what's going on right at the midpoint. So we want to calculate a stress there. We're going to say that this has a mass of 100 kilograms. I don't know what the density of this material would have to be for that to be possible, but just bear with me on that. And if this is the cross section, we have a height of 10 centimeters. And the neutral axis goes through the centroid, so it's right there. And we're going to calculate the stresses along that line. That's right at the midpoint here. So this is 0.025 meters. So we're going to calculate our stress tensor here. Okay, so, and same with this. We're going to calculate the stress tensor at the middle along the long axis. And half of the way up from the neutral axis to the top. Okay, well, since we're only doing it at one x value, I'm not going I'm not going to do a general cut. I'm just going to do the cut right at that point. You know, so our cut is just going to be for x equals 1 meter. This is half of the beam, so the weight force is just going to be half of 981, you know, half of the total weight, and it's going to act right at the middle. So this is 490.5. And then we have tension, shear force, and bending moment. Anybody have any questions about my setup on this? Newton's second law says 0, negative 490.5 plus t negative v is equal to zeros. So t is 0. V is negative 490.5. Okay, so t is 0. V is negative 490.5. And then the moment equation the distance from the left end, so here's my about point. The distance from the left end to the 490 is, the length of this whole piece is 1 meter, so this is half a meter. And that is a clockwise moment, so minus 0.5 times 490.5 plus m minus Vx is equal to 0. So m is equal to Vx plus 245.25. And so the bending moment along this line is negative 4. Oh, and I'm just in the habit of writing this as Vx, but x is 0.5. No, x is 1. So this is just V times 1. So m is equal to negative 245.25. Does that make sense? Yes. Okay. So first, stress due to tension. That's obviously equal to 0. And so this stress tensor due to tension is just zeros. Now due to the bending moment, our formula is sigma xx is negative m y over I. So we have to calculate that area moment of inertia. I is equal to 1/12 times the base, and which I didn't give, but I meant to. This is 2 centimeters. So 1/12 times 0.02 times the height cubed. The height is 0.1 meters, so 0.1 cubed. And you get a value of 1.6 repeating times 10 to the minus 6. So sigma xx is equal to negative of the bending moment, which is negative 245.25, times y, the height of the desired point above the neutral axis. Remember, this can be positive or negative. In our case, it's going to be positive, and that distance is 0.025. I'm going to put that positive in there just for clarity. And then we're going to divide by 1.6 repeating times 10 to the minus 6. And you get 3.68 times 10 to the 6. And so the stress tensor due to bending is 3.68 times 10 to the 6, 0, 0. And now the stress tensor due to the shear force. We have an XY shear stress, and it's equal to V times Q minus IB. We already have everything except the Q. Okay, so here's the neutral axis. There's the line that we want. This distance is 0.025. This is 0.02. The centroid of this area is right in the middle there. So this distance is 0.025 to get to the bottom of the shaded rectangle, plus another 0.0125. So this D is equal to 0.0375. And so Q is equal to 0.0375 times the area of that rectangle, 0.025 times 0.02. And you get 1.875 times 10 to the minus 5 meters cubed. Yep.
Earlier, did you define the section when right above the neutral axis as being 0.025?
Since it's right in the middle, these two are,
Oh, they're the same. And then
yeah, it's
you
the
add
same,
half of
exactly,
it.
exactly. It doesn't have to be, but in this case it was. Maybe I should have chosen a different point to be clear, but.
And it doesn't matter, and you don't have to put it on point that's moving.
No, right. Yeah, you can do any point. And actually what this means, if you think about that, the meaning of that Q, it means that the stress due to shear at the top,
Mhm.
what's the Q value at the top? Like what's the area of the stuff above the top, you know?
Oh, 0.
0. And so Q is 0. And so at the top, you don't get any stress due to shear. Same with at the bottom.
Okay.
If you put the line at the top and then you use the other form where you calculate the area of
Yep.
it.
So then the centroid is at the neutral axis,
Oh.
so your D is 0. Yeah.
So you have the most stress, right, in between.
Yes, the most stress due to shear is at the neutral axis.
So it would be kind of like a.
Yeah, right. I find it hard to represent that stuff, but if you, it would be like, you know, if that represents the shear stress, it would be 0 at the top and bottom and biggest in the middle. I'm erasing. Yeah. I'm definitely erasing that. Okay, I'm never. Mental note, don't draw that again. Okay, so now tau xy is equal to, what was our shear force? Negative 490.5. So we have negative of negative 490.5 times Q of 1.875 times 10 to the minus 5 divided by the area moment of inertia that we did in the last one, 1.6 repeating times 10 to the minus 6 times the thickness of the cross section at the line we want. This is a rectangle, so we don't care. If we're doing the circle at the neutral axis, it's going to be the diameter of the circle. So this is 0.02. And we get a value of 2.76 times 10 to the 5 pascals. And so the stress due to shear force is equal to 0. 2.76 times 10 to the 5, 0. 2.76 times 10 to the 5, and zeros everywhere else. And now put it all together. The total stress tensor is the sum of these three, which is 3.68 times 10 to the 6, 2.76 times 10 to the 5, 0, 2.76 times 10 to the 5, and zeros. And now you can do all the stuff that you are used to being able to do with stress tensors. You can find the principal stresses, find the maximum shear stress, express it about different coordinate systems, all that stuff. Yes?
The last one you have to do is torque.
The last one we have to do is torque, yep. And there are two types of cross sections we'll do for that. But
and it'll be the stress total stress that you showed at the very beginning of the small part.
yeah, right, exactly, yep. And there's a couple of extra little complexities for doing the torque, but you know, any internal loads calculation that we did in statics, you can now do the stresses for at any point. So, but
And then that would be a point. along the, so it changes as you move up and down.
Right.
And so.
Yes. Yep, that's right.
For like something that's short and fat, does it also change like horizontally? Is that why it's complicated?
Yeah, because it starts to, you start to get warping. One of the things you need is that you need sections that start out plane to be plane after the deformation. And if you have a wide, short thing, those start to warp. So the assumptions don't work and these calculations don't work.
So what the hell do we do?
So what do you do in practice is, I mean, like if you work for a company that needs to know this stuff, you'd probably never do these calculations by hand anyways. You do it by finite elements. I mean, mathematicians, like mechanics people, can by hand do more complicated things like this, but you can't do the most complicated stuff. So in practice, everyone uses finite elements. And really all we're trying to do is just get a good understanding of what these things mean, how they relate to each other. So when you get finite elements results, you can make sense out of them, you know. Also, it's a way to sanity check some things. Like, okay, if you have something that's short and fat, like you said, you do this approximation, then compare it to your finite elements. This won't be very trustworthy, but at least you can tell whether your finite element stuff is bonkers, because it's pretty easy to get bonkers finite element results, especially if you're not like an expert in using finite element software.
Is finite elements software programmed using this stuff or different approaches?
Let me try to remember. Finite element calculations are divided up into linear and nonlinear stuff. Obviously, only linear calculations relate to anything we're doing, because we're only dealing with the linear region of the stress strain curve. So for the calculations, for the linear part, the calculations are very similar to this. I don't remember if they're exactly like this or not, but they're very similar. And then for the nonlinear stuff, they're pretty different. But yeah, the basic idea is that you break it up into little pieces, like any numerical algorithm. You break it up into little pieces, and then you do the simple calculation on the little pieces, but that gives you a complicated view of the whole thing.
Yeah.
Okay, that's all. Spring break, woo! Yeah.
What are the reaction characteristics of a slot joint experiencing support?
A slot joint.
So specific.
That is. Is that something you're working on, or are you just curious about?
We never really talked about that. Like what you're doing.
Yeah, can it support a torque?
Like how does that work?
Yeah. Well, that starts to get into how the actual joint, like you can make slot joints in a bunch of different ways, and it starts to get into, okay, what specific way are we doing it? What materials are we using? What other things are there? So I don't think there's really one answer for that. Some, like slot joints, can support a torque, but they're not designed to do it very well. You wouldn't want to depend on it to support a very big torque, you know, or you just start to bend your slot and bend your little pin or whatever, you know. But other than that, that's probably the best answer I can give, kind of a non-answer.
Some of the, I think it's crazy, all these linkages and all the math, and all this stuff, like some of the designs I've seen.
Yeah.
On some of these airplanes,
Mm-hmm.
especially MD-11 back in the day, I couldn't imagine the engineering,
Yeah.
mathematical, it's not just done by a lot of people done by hand. You know,
Uh-huh. Yeah.
to have as much of assisted,
Right.
and it's just insane to me.
It is insane.
Now everybody's got an easy world.
Yeah. Right. You got it easy now, and I mean, people need to know this stuff who are